Hello everyone, I'm Dr. Meena Arora from JSS Academy of Technical Education, Noida. I'll be delivering lecture on Input-Output Management and Scheduling, Unit 5 of Operating System, KCS 401 for second year students. I'll be referring to PDF file of William Stallings, an author whose book is referred for this particular syllabus. I'll be sharing you the slides of this PDF file. Input-Output Management. Categories of input-output devices. There are three types of categories: human readable, machine readable, communication. External devices that engage in input-output with computer systems can be grouped into three categories. First is human readable. Those devices which are suitable for communicating with the computer user. For example, printers, terminals, video displays, keyboard, mouse, all comes in the category of human readable. Second is machine readable. Those devices which are suitable for communicating with electronic equipment like disk drives, USB keys, sensors, controllers. The third is communication. Those which are suitable for communicating with remote devices, for example, modems, digital line drivers. These are three types: human readable, machine readable, and communication. Now, what are the difference, or on what basis these three differ from each other? Differences in input-output devices. These devices differ in number of areas, data rate. There may be differences of magnitude between the data transfer rates, application. On the basis of application, that is the use to which a device is put has an influence on the software. Third is complexity of control. The effect on the operating system is filtered by the complexity of the input-output module that controls the device. Fourth is unit of transfer. Data may be transferred as a stream of bytes or characters or in larger blocks. Fifth is data representation. Different data encoding schemes are used by different devices. Sixth and last is error conditions. The nature of errors, the way in which they are reported, their consequences, and available range of responses differs from one device to another. Now, what is the organization of the input-output function? The three techniques for performing input-output are: first is programmed input-output, second is interrupt-driven input-output, third is direct memory access. In program input-output, the processor issues an input-output command on behalf of a process to an input-output module. That process then busy waits for the operation to be completed before proceeding. Interrupt-driven input-output, the processor issues an input-output command on behalf of a process. It's of two types: if non-blocking or if blocking. If it's non-blocking, processor continues to execute instructions from the process that issues the input-output command. If blocking, the next instruction the processor executes is from the OS, which will put the current process in a block state and schedule another process. The third technique is DMA, direct memory access. Here, a DMA module controls the exchange of data between the main memory and an input-output module. Evolution of the input-output function. First is processor directly controls a peripheral device. Second is a controller or input-output module is added. Third is same as two, that means a controller or input-output module is added, but now interrupts are also employed. Fourth is the input-output module is given direct control of memory via DMA. Fifth is the input-output module is enhanced to become a separate processor with a specialized instruction set tailored for input-output. Sixth is the input-output module has a local memory of its own and is in fact a computer in its own right. Now there's a diagram for DMA, direct memory access. There are four different blocks in it: data count, data register, address register, and control logic. And there are flow lines also. Data lines and address lines are bidirectional. The other lines, request to DMA, acknowledge from DMA, interrupt, read, and write, are unidirectional. Now, what are the design objectives? Design objectives are basically based on two things. One is efficiency and second is generality. If we measure the design objectives on efficiency, then it comes major efforts in input-output design. Second, it's important because input-output operations often form a bottleneck. Third, most input-output devices are extremely slow compared with main memory and the processor. And the last is the area that has received the most attention is disk input-output. And on the basis of generality, we can say it's desirable to handle all devices in a uniform manner. then applies to the way processors view input-output devices and the way the operating system manages input-output devices and operations. Then diversity of devices makes it difficult to achieve true generality. Then use a hierarchical modular approach to design of the input-output function. So the two design objectives are like this: efficiency and generality. As we have studied, as we have read here, use a hierarchical modular approach to the design of input-output function. We'll study the hierarchical design. Functions of the operating system should be separated according to their complexity, their characteristic type, scale, and their level of abstraction. Hierarchical design itself means a multiple level design, multiple layer design. So it leads to an organization of the operating system into a series of layers, and each layer performs a related subset of the functions required of the operating system. Layers should be defined so that changes in one layer do not require changes in the other layers. Then comes buffering. Buffering performs input-output transfers in advance of request being made and perform output transfers sometime after the request is made. Block-oriented device and stream-oriented device. Buffering can be done by these things. Block-oriented device stores information in blocks that are usually of fixed size. Transfers are made one block at a time. It's possible to reference data by its block number, as there are many blocks, so we can refer every block by its block number. Disks and USB keys are the examples of block-oriented device. Stream-oriented device transfers data in and out as a stream of bytes. No block structures are required here. Terminals, printers, communication ports, and most other drivers that are not secondary storage are examples. You must have noticed this in printers this time. Now, there are four categories: no buffer, single buffer, double buffer, and circular buffer. For no buffer, it is without a buffer, the operating system directly accesses the device when it needs. The block diagram shows input device, then operating system, there is no buffering here, and then user person. For single buffer, if you see, there is a buffer in operating system. Operating system assigns a buffer in main memory for an input-output request. Block-oriented single buffer. Input transfers are made to the system buffer. Reading ahead or anticipated input is done in the expectation that the block will eventually be needed. When the transfer is complete, the process moves the block into user space and immediately requests another block. It generally provides a speed up compared to the lack of system buffering. And the disadvantages are complicates the logic in the operating system. Swapping logic is also affected. Stream-oriented, as we already studied, there are two types: block-oriented single buffer and stream-oriented single buffer. In stream-oriented single buffer, line at a time operation, byte at a time operation. In line at a time operation, it appropriates for scroll mode terminals. User input is one line at a time with a carriage return signaling the end of line. Output to the terminal is similarly one line at a time. In byte at a time operation is used in the form mode terminals when each stroke is significant, other peripherals such as sensors and controllers. Double buffer. In double buffer technique, it uses two system buffers instead of one. Here, in case of block diagram, you must have seen there are two buffers. A process can transfer data to or from one buffer while the operating system empties or fills the other buffer, also known as buffer swapping, as the two buffers are used and buffer swapping is done. Now, circular buffer. Two or more buffers are used. Each individual buffer is one unit in a circular buffer. In case of circular buffer, you see there are many buffers and there is a circular queue maintained here. Two or more buffers are used. Each individual buffer is one unit in a circular buffer. It's used when input-output operation must keep up with the process. This was about circular buffer. Now we'll see all these four at a stretch: input-output device with no buffering, input-output device with single buffering, input-output device with double buffering, and input-output device with circular buffering. All these four diagrams are shown on a single screen. Now, what are the utility of buffering, or what is the utility of buffering? Technique that smooths out peaks in input-output demand. With enough demand, eventually all buffers become full and their advantage is lost. When there is a variety of input, output, and process activities to service, buffering can increase the efficiency of the operating system and the performance of individual process. So this was all about buffering and input, output methods. That's it. Thank you. Thank you, everyone.